Hi, in this video we're going to represent an AR as a GLP. That is an autoregressive P model as a GLP. Here is the AR2 that we're going to show it here as in our example. And the first thing we're going to do is put it into backshift notation. So that'll be 1 minus 1.6b plus 0.8b squared xt equals at. xt times 1 is xt. xt operated on by b is xt minus 1. There's the minus 1.6. xtb squared, xt minus 2. There's the 0.8. We are good. Okay, so now if I want to represent this as a GLP, I'm essentially representing it as an MA. And thus, just through algebra, we will have xt equals, and there's really a 1 right here. So that's 1 divided by 1 minus 1.6b plus 0.8b squared at. Now I'm doing something that is going to be practically useful but mathematically not quite sound, and that is, remember that b is the backshift operator. It's not a variable. So I'm going to end up doing polynomial division here as if b was a variable, but remember that it's an operator, but that's going to become practically useful for us. As we'll see here in a moment. So I'm going to keep that as a b. And if I can just find out what this equals, then I'll have how to transform xt, or how to operate on at to get this relationship. So what I'm going to have to do here, though, is do some polynomial division. And that will be 1, right here, 1 divided by 1 minus 1.6b plus 0.8b squared into 1. Okay, so this is nice. The way we do this is we just say, hey, what do I multiply 1 by to get 1? Well, that's pretty easy, and that's just 1. So this will be 1 times 1 is 1. 1 times 1 minus 0.6, and we're going to end up playing this game several times. But once we see it once, we just repeat it. And remember that this is really plus 0b plus 0b squared, and we'll add the terms as necessary. So, awesome. So what we're going to do here is, remember that this is another big piece of this that is commonly forgotten. We're going to subtract this whole thing here. So I'm going to put a minus and put that around it so we remember that we're going to distribute that negative sign. So that's 1 minus 1 is 0. That's 0 minus negative 1.6b is 1.6b, and 0b squared minus positive 0.8b b squared is minus 0.8b squared. And we have completed one full kind of iteration here of polynomial division. So we'll just repeat from here and we'll say, okay, well now we've got this. So what do I multiply 1 by to get 1.6b? Well, that's just 1.6b. So 1 plus 1.6b. Already kind of got our divisor here, or our quotient. And so this is 1.6 times b times 1 is 1.6, which is why we chose it to be exactly that. And we have 1.6, positive 1.6 times negative 1.6, and that is negative 2.56. And that's b times b is b squared. Negative 2.56b squared. Okay, and then I will have 1.6 times 0.8. So 1.6b times 0.8b squared, which is about 1.28. 1.28, and that will be positive. Positive 1.28b squared, b cubed. Right, b times b squared is b cubed, and that's plus 0 b cubed, and we do another subtraction across that whole expression. Okay, so now 1.6 minus 1.6b minus 1.6b, great, that's why we chose it, it cancels out. Negative 0.8b squared minus negative 2.56b squared. So that'll be a negative 0.8b squared plus 2.56b squared, which gives us 1.76b squared. And then an easy one here, 0b cubed minus positive 1.28. That's minus 1.28 b cubed. Great. And we've done round 2. Now we're in for another one, another iteration here. So let's play the game again. So what do I multiply 1 by to get 1.76b squared? Well, that's simply 1.76b squared. And there we have that. And so now we need to extend this. We'll probably go one more, but 1.76b squared times 1 is 1.76b squared. And that's why we chose it. So 1.76b squared times 1.6b, negative 1.6b, and that will turn out to give us negative 2.816b cubed. So negative 2.816b cubed, and then we'll have 1.76b squared times 0.8b squared, and then it'll give us 1.408 and positive 1.408b to the 4th. And remembering here that that will be a positive 0b to the 4th. And we're ready to do our subtraction. We're going to subtract the whole thing. And that will give us 0, 1.76b squared minus 1.76b squared. Again, that's why we chose it. Negative 1.28b cubed minus negative, so that'll be a positive. And that will turn out to be 1.536b cubed. Positive 1.536b cubed. Yep. And then 0 minus 1.408b to the 4th. That's minus 1.408b to the 4th. Great. And so we'll make this our last one, but we can see what our next piece of the quotient is up here. This will be, what do I multiply 1 by to get 1.536b cubed? That's plus 1.536b cubed. Great. And so, and that just kind of goes on and on and on, right? We can keep playing that out. And likely it just goes on to an infinite number of terms. So what do we have now? So again, mathematically, right, this is an operator, but I'm treating it as a variable here for practical purposes. That's exactly what I need here on top. So what I've got is I have xt. This is xt in backshift notation. And so I have xt equals this function of at's. And so I'm going to go ahead and put that down here, see what we've got. So this is really, make that right there, xt, kind of just spelling it all out, equals, what have we done? Well, we've said that it equals 1 over 1 minus 1.6b plus 0.8b squared. Said, okay, but do we know that? Yeah, we did the polynomial division. So that's at equals, and that will be approximately, let's make that approximately 1 plus 1.6b plus 1.76b squared plus 1.536b cubed. And that's approximately, right? So we'll just have that out to 3 terms times at. So then what do we have here at the end of the day? We have that, we'll just put that here, equals at plus 1.6 at minus 1, right? At times b, and are operated on by b, plus 1.76 at minus 2, and then plus 1.536 at minus 3. And so at the end of the day, we have that we can represent xt approximately as, again, just rewriting that, put it all together, at plus 1.6 at minus 1 plus 1.76 at minus 2 plus 1.536 at minus 3. And we have written, and we have expressed this model, this AR model, this AR2 model, approximately as a GLP out to 3 terms. So And we've also introduced and reminded ourselves of this concept of polynomial division and its usefulness. So great work. We'll actually have some software that will help us. We're not going to have to do polynomial division every time, but it's good to know kind of mathematically what's going on behind the scenes behind that function. So great work. See you later.